mostly, I guess, this you could, in terms of the marks itself, it's only about 5 points. Each homework would be about 5 points on your final cumulative. But as I said, actually the homework problems are more interesting often than the test problems. And so you can learn a lot by actually looking at all the comments that he made. That's basically all I have to say about that. The solutions are already provided long back. Okay. And I said I'll send the statistics on it. But I believe highest was 65, 64. Those were the ones. Yes.
Do you know what's the plus and minus on the grading?
I think that he just basically made notes for himself and then he converted them to marks. Okay. Okay. Then, so are there any other questions about things that we discussed, for example, last time? Okay, so I'm going to continue the discussion of propositional logic, and this was the slide we were looking at last time, right? And then this was basically, if you remember, we were talking about the fact that we can do inference basically using models, model-based reasoning directly in terms of the models, or using inference rules. Okay, and if you have inference rules, you are interested in asking whether the inference rule is sound and complete. Okay, soundness means when the inference rule allows you to prove something, it is actually entailed in a model theoretic sense, because model theoretic sense is that the first principles idea. Okay, and the completeness is everything that is actually entailed can also be derived by the inference rule. Okay, so in fact, in this particular picture, we are using, so we are computing entailment. Entailment is written, the usual notation for entailment is this. Okay, so I'll say KB entails alpha. That means any word which is a model of KB is also a model of alpha. That's what entailment is. Okay. Now somebody is trying to sell you a cheap way to. The way to compute this, of course, is directly use the definition. As I said, the entailment definition is any word which is a model of KB is a model of alpha. So find all the models of KB and see that in each of those models alpha is true. That means the model of this is also a model of this. Okay, that's pretty much what we were doing using truth tables last class for the propositional logic. What we want to do next is we want to consider using some shortcuts where, for example, things like mod exponents, we'll see in a minute, where you get to syntactically look at the form of the knowledge base and write some additional sentences that you think are true given what is true in the knowledge base. And suppose you are using some inference rule I, okay, then you're saying, according to this inference rule, beta can be derived from the knowledge base. The reason you're doing this is because you are actually trying to compute this. Okay, so since this is the gold standard, the question is this really computing the gold standard or not? Okay, soundness essentially says, if you derive, then it is entailed. If you said beta is derivable, then beta is also entailed. Okay, completeness says, if it is entailed, it is derivable. That means if gamma is entailed, then this inference rule will also get you gamma. Okay, and if you have an inference rule that's both sound and complete, then it is essentially equivalent to doing entailment using that inference rule without having to go through the first principles. Okay, so that's basically where we are, and then we talked about the semantics of propositional logic. we talked about how to directly do model theoretic entailment in propositional logic. One of the interesting things is for propositional logic, the number of words is finite. Okay, because if you have n propositions, there are 2 power n words. Okay, and so you then have to check each of those words whether they are a model of this knowledge base. And for any one of those words which is a model of this knowledge base, you check if it's also a model of alpha. If so, you're done. Okay, so as bad as it might look, it's actually doable. It's a finite number of words. And if you remember several weeks back when we started the semester, I talked about the fact that if you can go from propositional logic to predicate logic, and then predicate logic to first order logic, and first order logic to first order logic. Basically, first order logic has also functions, and if you throw in a function, then in essence you have infinite number of objects. And if you have infinite number of objects, then you have infinite number of relations between those objects. That means there are essentially infinite number of propositions, which means for first order logic, direct computation of model theoretic entailment is impossible. Do you understand what I'm saying? In propositional logic, we will try this first, and we'll also learn this, how to do it. But eventually, when we go to first order logic, we will never be able to do this by hand. Or by, you can never do it by enumeration because there are infinite number of models. So in essence, you directly need to just do inference using inference rules. Okay, and then check whether, and then hope that basically what you're doing is sound and complete with respect to what the model theory would have said. Okay, which is the interesting part. But we'll get there soon enough. But right now, for propositional logic, let's look at inference rules. The inference rules are, here are some inference rules. Okay, these are all sound but incomplete. We'll see why they're incomplete in a minute. Okay, so one inference rule says if your knowledge base contains A implies B, and it also contains A, then you can go ahead and write B into the knowledge base. I guarantee you that B would be true. If in every world where A implies B and A are true, B is also true. B may be true in many other worlds, but it's certainly true in these worlds. Such modest ones. You know this, right? A implies B, and A, you get to write B. Okay? Then there is another inference rule called modest tolerance, which essentially says if you have A implies B, and you have not B, you can go ahead and write not A. Okay? And then you can also have a rule like chaining, which says if A implies B, and you have A implies B and B implies C, then you can go ahead and write A implies C. That'll be true. Now, how do I know? And then there is this other rule I have called abduction, which is kind of, I put a question mark, so we'll keep that in mind. What that is saying is A implies B and not A. Okay, can you go ahead and derive not B? Okay, this one says you can do it, but that's an inference rule. Inference rules can say anything they want. The only question is, remember that this entire lecture started with the Monty Python logic. Monty Python logic corresponds to a particular inference rule. It's up to you to figure out whether it is sound or complete. Okay, so now let's look at this. So you I basically think, you basically agree that this looks like a good rule, but how do you prove to yourself that this is indeed sound? You go back to the model theory. That's how you prove it. In propositional logic, it's easy enough to go back to the model theory. Okay, so for example, since this is simpler, then I'll just do this modest tolerance. Okay, so I use the truth table method. So here's my truth table: A, B, A implies B. Okay, and these are all the words: true, 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 false, false, true, false, false. And then A implies B in each of these: true, false, true, true. By the way, notice that an implication is actually false only in one of the words. This is not too obvious to people. Basically people tend to think of logical implication. You have to remember that a logical implication, A implies B, is equivalent to not A or B. That's what it is. It's equivalent. Which means implication becomes true if B is true. Okay? There are two worlds where B is true. B is true and A is false, and B is true and A is true. Okay? In both those worlds, not A or B is going to be true. So if B is true, implication is true. And if B is false, implications can still be true if A is false. Because if A is false, not A is true. And that is the point where actually a lot of people get confused. If you have a false, if your antecedent is false, then anything is derivable. So false implies anything. Okay? So that's what this is saying. So the only place an implication fails is you find a world where A is true, but B is false. That's when the implication fails. That can't happen. If A is false, it doesn't matter what B is. Okay? And if B is true, it doesn't matter what A is. The only time implication fails is A is true and B is false. That's the only place we have is false. Okay, now that is there. And then the knowledge base itself is A implies B and A. Right? So then I'm taking conjunction of these two columns and writing, knowledge base itself is A implies B and not B. This is what we are proving. Okay, so I'm basically doing shortcut. So this is true and not B is false. True and false is false. Okay, false and true is false. True and false is false. True and true is true. Right? So I have the knowledge base is true in only one word. So the knowledge base only has one model. The model for that is false, false. That's the only place. When A is false, B is false, then the knowledge base holds. In that case, what about not A? It holds. Okay? So the only model of the knowledge base, which is this green part, is also a model of not A. So I am actually sound in writing A implies B and not B entails not A. Do you see what I'm saying? It's a roundabout way, but once I prove it to myself once, then I can just be using it syntactically. Anytime I see A implies B and not B, I get to write not A. And of course, since this proof didn't depend upon the names of A and B, it also works if you have J implies K and not K. You get to write not J. Okay? Fine. Now, the reason, and using the same reasoning, you can show that abduction is actually unsound. Okay? The abduction is unsound because, I wrote the truth table here, and I essentially showed you that there are two worlds for the knowledge base. A false, B true, A false, B false. Both of them happen to be the models for the knowledge base. But only one of them is also a model of not B. This one is a model of the knowledge base, not a model of what you want to prove. You see what I'm saying? That is the reason why the entailment doesn't hold. And so in this case, if you use this rule, then you would be deriving certain things that are not actually entailed. So it's an unsound rule of inference. Okay? Right? And then, you can also, you can take as a homework assignment proving the soundness of chaining. You should be able to do this. If I give you an arbitrary rule, you should be able to tell me whether or not that is actually a sound rule. Now, this is how you prove soundness or unsoundness. Okay. How do you prove completeness? Now, so actually these are sound, I said. Here is a rule which is complete by itself, just complete. Okay? which is you ask me a question, I'll say yes. Any question you ask, I'll say yes. Okay? So you ask me, is A true? Yes. Is not A true? Yes. Is B true? Yes. Is not B true? Yes. Is A implies B true? Yes. So this is the yes ma'am inference rule. Okay? It's complete. Because every fact that is actually entailed, I would say yes to it. I'll say yes also to a whole bunch of other things, but I'll certainly say yes to the things that are entailed. So it's very easy to get complete rules that are not sound. In this case, obviously, this can't be sound because it's saying yes to everything. Okay? You can get sound rules which are not complete. And actually, I did give you an example as to why it is not complete. You can almost guess they're not complete because if any one of them is complete, then why do they need the rest? Do you see what I'm saying? If it to be for an inference rule to be complete, the point is you can keep just using that inference rule, and eventually you will derive every theorem just by using that inference rule. Right? Okay. So if modus ponens is so complete, why do I need modus tollens? Right? Okay. And in fact, none of these are complete by themselves. It turns out that in what is called natural deduction, which is basically natural theorem proving, what it does is it uses all these rules. It uses modus ponens, modus tollens, chaining, all these rules. Of course, not abduction because it's unsound. And then basically, use them until it writes all the things that are true. That is possible. So, as a group, it turns out they are complete. But not any single rule is complete. Okay? And to get an example to understand that, in fact, so you can easily get just complete, you can easily get just sound. One question, and pretty much everything on this part you've seen this before. But probably most of you, at least a large number of you probably did not hear about a rule that's both sound and complete for propositional logic. So that would be an interesting bit you'll hear today. In fact, the next slide. Okay. So to get an idea as to where these guys will stop being complete, and in particular where modus ponens by itself would not be complete, okay, consider the following example. If Will goes to the party, Jane will go to the party. If Will doesn't go to the party, Jane will still go to the party. Okay. Now my question is, will Jane go to party? Do you see whether Jane will go or not go? You can see that she goes, right? Can you use modus ponens to prove this? No. Because I did not tell you, if I said W implies J and W, then you could have written a J. And if I said not W implies J and not W, you could have written J. But I didn't do that. Okay? Instead, what I basically said is W implies J, not W implies J. And you obviously know not W or not W is true. That's, W can be either true or false. So W or not W is true. And so what you did in your mind when you figured out that Jane will go to the party is you did a case analysis. You said, let's consider the case where Will goes to the party. Then what happens? Jane will go to the party. Now, let's now consider the case where Will doesn't go to the party. Then what happens? Jane still goes to the party. I have now considered all possible cases. So I have proved that Jane will go to the party. Okay? That's what modus ponens doesn't do for you. It doesn't do case analysis. In general, case analysis increases the cost of inference because there can be a large number of cases. And you have to consider all possible cases and make sure that in every case this is true. Okay? Doing that systematically requires, obviously, a different kind of inference. Modus ponens can't do it. Okay? So this is the classic example of why modus ponens is not enough. In fact, modus tollens also is not enough for this. Okay? So what you need is you need to do case analysis, and it turns out that there is this rule called resolution rule, which if you just keep applying the resolution rule, you would be complete as well as sound. Okay? And so that's the one that we'll talk about. So the resolution rule is of the following general form. If you have a formula alpha or beta, and another formula not beta or gamma, then you basically remove beta and not beta and write alpha or gamma. That's what the formula, that's what resolution rule is. Looks simple enough, right? So, and of course, obviously, there's nothing sacrosanct about alpha, beta, and gamma, the names. So I could write, if I have A or B, and it's actually useful to write it like this, not B or C. Then I resolve these two, B or not B just disappear. I write A or C. Okay, the first question is this sound? I say that it is sound, and your homework assignment is to prove to yourself that it is sound. Because in fact, in this case, you need to write a truth table of 8 rows. Right? And then find the rows where A or B and not B or C together evaluates to true. And those would be the models of this. And check to see that in all those models A or C is true. When you did this, then you proved to yourself that resolution is sound. Right? Okay? Now the other interesting thing about resolution is it's actually subsumes every other rule you have seen. Okay, so for example, I have remember A implies B and A, then I get to derive B, right? Well, what is A implies B? Not A or B. Resolve it with A. Right? Okay. And what about modus tollens? A implies B and not B. You get to derive not A. So you have not A, not B, not B. So this actually subsumes everything. Okay, everything that other guys can prove, this guy can prove too, basically. Okay, now to show that it is actually complete, I need to do an inductive proof. The textbook has a nice sketch of it. I suggest that you look at it. Okay, right now I'm just saying, proof by citation to eminent authority that it is complete. Okay, but the way you actually show that it's complete for propositional logic, the proof is easy enough to understand. It's a proof, inductive proof. Okay. Now, one thing I am sort of pushing under the rug is I'm expecting a certain form for all my formulas. The formulas all should be of the form a literal, there should be disjunction of literals. What's a literal? A literal is a proposition symbol or a negation of a proposition symbol. And a formula now is going to be a clause. A clause is a disjunction of literals. Literal 1 or literal 2 or literal 3, where literal 1 can be P or not P, and literal 2 can be J or not J, etc. Okay? Now, I'm sort of assuming that all formulas must be in this form. Now, if you can tell me that, well, there are propositional logic formulas that will never get into this form, then I'm dead. Right? Okay. Thankfully, it turns out that the clausal form happens to be a canonical form. And in fact, in a minute, I'll show you a little procedure which can take any arbitrary propositional logic formula with all sorts of implications, negations, conjunctions thrown in, and you follow this form, procedure, you will end up with a set of clauses. Okay, you can see that it can be done, at least in some cases, because you just did this here. A implies B became not A or B, which was in the form you wanted. Right? And I'll tell you a general procedure about doing this, and that's why it's called, this is basically called CNF, conjunctive normal form. It's actually a normal form, not canonical form. A normal form, everything can be converted back into CNF. In fact, there are other canonical forms, other normal forms we'll look at in a minute too. But we care about CNF, and resolution is written in terms of CNF rules, CNF clauses. Okay. Now, and in fact, if I'm using the resolution rule, and I'm saying that it's complete, so in fact, two things you can do in trying to prove a theorem that you want to prove. Okay. So you convert your knowledge base into clausal form. Okay. And then you keep doing resolutions. Just keep doing resolutions until you find, as a result of one of the resolutions, what you wanted to prove. Okay, and then you're done. That's going forward. The other idea is you assume, and you want to see whether, let's say you want to prove beta, you negate beta, convert it into clausal form, add it to the knowledge base. Now it must be, if in fact beta was entailed, then adding negation of beta to the knowledge base should make knowledge base inconsistent, right? So then if I keep doing resolution on that knowledge base plus negation of what I'm trying to prove, at some point of time I should be able to derive false. I should be able to derive false. Now how does false look in resolution? In clausal form, how does false look? Let's see. Suppose I have A and not A. That's a clausal, that's going to be false, right? If my knowledge base has A and not A, it would be false. Okay? So if I use resolution A and not A, then in a sense I'll get an empty clause. Because A and not A went away, I have nothing left. So I have an empty clause. Because it is that an empty clause is just how false looks. So if you ever get an empty clause, as you keep doing these resolutions, if you ever get an empty clause, then you say, yes, I'm done. I am actually able to prove what I wanted to prove. Okay? In some sense, this is like basically the basic idea of proof by contradiction. You're trying to prove beta. Let's assume beta is not true. Then I prove that there is no world where the knowledge base is existing, knowledge base holds and beta doesn't hold. So that means when I gave negation of beta and added it into the knowledge base, I have a new knowledge base for which there are no models. Okay, now here is an interesting question. What if my original knowledge base was already inconsistent? So the idea here, the intuitive idea here is the knowledge base itself was okay, and knowledge base, you're trying to prove that knowledge base entails alpha, entails beta. So you negated beta, added to the knowledge base, you have a new knowledge base called KB plus not beta, and then you are able to get an empty clause. What if knowledge base itself was already, inconsistent? That means my knowledge base is A and not A. Fine. It will, in that case, of course, you will say everything is provable. But that's what we agreed. The definition was that, in fact, if your knowledge base has no worlds, which are its models, then, trivially, every theorem is proved. Because all you care about is every model of the knowledge base must also be the model of what you're trying to prove. And if your knowledge base doesn't have models, fine. Everything is proved. Okay, so that's basically, so you can use resolution in the forward way until you reach the theorem, or you could do it in the reverse way, which is proof by contradiction, where you add the theorem that you want to prove in the negated form and keep doing resolutions until you get an empty class. So this empty class, and it turns out, we'll see in a minute, that it turns out that this is actually the preferred way to use resolution. Why? Because if you use resolution the forward way, then you can't just use resolution. You have to use resolution plus a few more logical equivalence rules. And then it will be complete. Whereas if you are using resolution in the backward way, the resolution refutation, then just using resolution you will get to an empty class, if in fact the original theorem is provable. So that's why we look at this. Okay? And also, one other interesting thing is, this forward is you just proving, making more and more inferences and hoping one of them will be what you wanted to prove. Whereas if you throw in what you want to prove in the negated form to the knowledge base, then that can be used to focus your search for empty class. I use the word search for empty class. And we'll see in a minute that getting empty class is not obvious. In fact, even a simple example, I have a little simple animated example, and that will mess with your brains because there's so many resolutions you have to do until you get an empty class. In general, theorem proving is not supposed to be easy. Why? Because we pointed out at the end of last class that for propositional logic, theorem proving is basically equivalent to saying a particular knowledge base has no models. The knowledge base KB plus not beta has no models. So theorem proving is the conjugate of Boolean satisfiability problem. Boolean satisfiability is NP complete, which means everybody assumes that there is now better than an exponential solution for it. So that means theorem proving is also exponential. Do you see what I'm saying? Okay? So you don't expect any miracles. It's supposed to take time. Right? Okay. So anyway, that's basically where we are in terms of resolution. Now, for this example, Will goes, Jane will go, and if Will doesn't go, Jane will still go. So then this becomes not W or J, because W implies J, which becomes not W or J. And this becomes not W implies J, that is not of not W is W or J. Now, if you resolve those, then you will get what? You won't get J. You'll get J or J. And so you have to use a logical equivalence which says J or J is the same as J. I mean, what is obvious to you is not obvious to your program. Right? If you use this in the forward direction, you'll get J or J, and then you need to throw in one extra step. Oh, by the way, J or J is the same as J. And then you'll be done. Okay? If you go in the refutation way, then what do? You take not W or J and W or J, and then you also add not J, because you want to prove that Jane will go to the party. So you take the negation of Jane going to the party, not J, add it to the knowledge base. Now I can do a bunch of resolutions, and then I'll get an empty class. Do you see what I'm saying? So in this particular case, what did I do? I took not J and W or J, not J and not W or J, I get not W. And then I resolve not W with W or J, okay? And I got J. Then I resolve J and not J, I got empty class. Okay, now, by the way, the temptation is overwhelming when you're doing this yourself to stop right there, because now J is there. Okay, that doesn't mean anything. You need to get the empty class. If you're going in the forward direction, you got a J, you can stop. If you're going in the reverse direction, if you're going in the refutation direction, your goal state is empty class. Until you get an empty class, you can't stop. Okay? So that's basically the use of resolution. One other thing that, while we are here, another thing that I want to say is this. suppose I have P or J and not P or not J. And if I resolve these, what do I get? How many of you think it is empty class? Just because I asked doesn't mean that it must be a trick question, although it probably is. But clearly, so this is basically saying either P is true or J is true. And this is saying either P is not true or J is not true. They are not inconsistent. There are worlds where both of them are true. And if there is a world where both are true, then it can't be inconsistent. Okay, the reason you are doing empty class is because you say, oh, there's a PRJ and there's a not PRJ. But remember what the resolution said. It only said you pick a beta and a negation of beta, and only those go away. So you choose which one are you going to resolve on. In this particular case, you can resolve it in two different ways. One is you can pick J as the resolvent, J as the literal you're resolving on, in which case you get P or not P, which certainly is not empty, right? Or you could resolve it this way, P and not P can be resolved away, and I'll get J or not J. That's what you are getting. Okay, the reason I brought this up is because under stress, people are desperately trying to look for empty class, and they will make one up, even if it involves actually using an eraser to erasing everything until it becomes empty. Okay, but there are only legal ways to bring up empty classes, and this is not one of them. And there's a reason. It's not like I'm just making this up. You can understand why it doesn't make sense. The resolution rule basically says you get to pick a literal and its negation and then resolve them away. That's it. Okay. Fine. So in fact, really what your intuition was saying was you're sort of thinking this itself is the negation of this, but it's not. Okay? In fact, your intuition is right. If I told you PRJ and I told you not of PRJ, then I can say empty class. Which you will never see in normal resolution, because normal resolution would essentially not allow you to have this as a class. This is not a class. Not of PRJ is not a class. So instead of this, you would have gotten something which puts the negation in. So not of PRJ can be written as not P and not J. But not P and not J is also not a class. However, it is two classes. Right? So what you actually have is you have not P and not J and PRJ. If I give you those three, yes, you can get an empty class. Right? First you can do this, you get a J, do this, you get an. You see what I'm saying? So that's what went wrong was, you just sort of assume that not P or not J is the negation of P or J, but it isn't. Okay, fine. So there is implicit in all our discussion today was any random formula can be converted into clausal form, right? And I basically want to discuss that now, and that there is actually a way to do that. So in particular, it turns out that there are multiple normal forms for propositional logic, one of which is this normal form called conjunctive normal form, which we are interested in. And a conjunctive normal form is basically a conjunction of clauses where each clause is a disjunction of literals. Okay? And in computer science, if they say Boolean clauses, they mean CNF normally. Okay? There is an alternate form called DNF, disjunctive normal form, where you have a disjunction of conjunctions. So the clauses will be conjunctions. Okay? And the disjunction is between the clauses. In the conjunctive normal form, the clauses have disjunction, They're basically disjunctions of literals. And all these clauses are conjoined. Okay? In general, because they are in the CNF form, you never actually write the and sign at all. When you have an and sign, that means it's a new clause, so you write it below the previous clause. Okay? So in the CNF, you will never see anything other than negation and disjunction. Conjunction is implicit. What happened to implication? We never needed that anyway, because implication, as I said, was syntactic sugar. It can be compiled away. Okay? In the DNF, on the other hand, you will never see disjunction. I'm sorry, in DNF, you never see disjunction directly. Essentially, each clause is a conjunction. And then all clauses are disjoint implicitly. Okay? Okay, so we'll focus on getting into this form. In fact, anything can be converted into either this or this, and we will understand how to convert it into CNF, because that's what we came right now. Okay? So the rules are very simple. Essentially, you do these steps. You start by first removing the implication. If you remove the implication, basically you do not of A. A implies B becomes not of A or B. Okay? Then you pull negation in. Pulling negation in essentially means if you have a negation over anything other than an atom, anything other than a proposition, that means if you have a negation over a group or a negation over a formula, then you can pull the negation in like we just did earlier. And so negation of P or Q would become negation of P and negation of Q. And similarly, negation of P and Q becomes negation of P or negation of Q. Okay, and then the last part would then be to if you have A and B or C, then you can write it as A and B or A and C. Similarly, A or B and C. The emergence laws. If I have A, R, B, and C, right? I can write it as A, R, B, A, R, C. Okay, basically, in fact, you write it as A, R, B, and A, R, C. And after these steps, you essentially will have clauses. And now you just ignore the and then split clauses at the end. That's the steps you're supposed to do. Okay? Let me do one example, the one that on the board. I mean, we did a bunch of examples already, actually, but let me do one example that's on the board to see how it works. So I'm doing this, not P and Q implies not R, R, W, right? Okay, so my first step is getting rid of the implication sign. So not of this or this. Okay, not of this is not goes away. So it will be P and Q are not R, R, W. Now my next step is bring all the implication, bring all the negations in, pull it so that they apply directly to a single proposition. Okay, so this is the only place where you have that. So this basically will become P and Q are not R and not W. Okay, you can write it. You can put that. Okay. Now, basically, okay. Now I do the last part, which is distribute conjunctions over disjunctions. Okay. So, for example, P and Q are not R and not W. So this can be written as P and Q are not R, and P and Q are not W. this in itself can be written as P R not R and Q R not R. This in itself can be written as P R not W and Q not R. So now this is class 1, this is class 2, class 3, class 4. Okay, so this corresponds to this set of 4 classes. Okay, it's only what 1, 2, 3, 4 elements, right? So in fact, you need to prove to yourself that this is true. I just did it, right? I mean, you shouldn't trust me. So you should prove to yourself, and the way to do it is write a 16-row table. Okay, and in a 16-row table, basically why 16 rows? Because there are 4 propositions, 2 power 4, right? 16 rows. And then in each of the rows, evaluate this entire formula, evaluate this entire formula. This is basically conjunction of these. And show to yourself that they both have the exact, those 2 columns are exactly the same. That's logical equivalence. Entailment is not logical equivalence. Entailment says where the knowledge base is true, alpha is also true. Alpha could be true many other places, but as long as it's true where the knowledge base is true, you're fine. To show equivalence, to say that this knowledge base is the same as this knowledge base, you have to say every model of this knowledge base is a model of this knowledge base and vice versa. That's logical equivalence. So in fact, logical equivalence has bidirectional entailment. KB1 entails KB2, KB2 entails KB1, that means they're equal. Okay? So it turns out that this one actually corresponds to these 4 classes. And you can prove to yourself. Okay? But basically I'm saying this can be done. Right? And you can actually just write a program. I mean, here I did it by hand, but you can write a program which in a polynomial time converts any arbitrary propositional knowledge base to a clausal form. Okay, and then if I give you a goal to be proved, then you first negate that goal, convert that too into a clausal form, add it to the mix, and then start doing the match chase for the empty class, which is what I'm going to show you now. Okay, so I'm going to do a non-trivial example now for propositional logic. Here is my English statement of the problem. Okay, if the grass is wet, then it's either raining or sprinkler is on. If it's raining, then Timmy is happy. If the sprinklers are on, then Timmy is happy. If Timmy is happy, then he sings. Timmy is not singing. Okay, prove that grass is not wet. Okay, right? So I'm going to write this into first I want to write this knowledge base into a propositional logical format. So I basically invent propositions. So grass is wet would be a proposition. Raining would be a proposition. Sprinkler on would be a proposition. Timmy singing is a proposition. Right? So here are my rules. Here are my first order logic things. I'm sorry, propositional logic statements. Up front, it's better to write them in the natural form, the way you think, and then convert them into clausal form. Okay? So grass is wet, then either it is raining or the sprinkler is on. GW implies R, SP. If it's raining, then Tim is happy. R implies TH. If sprinklers are on, then Tim is happy. SP implies TH. If Tim is happy, then he sings. TH implies SG. Tim is not singing, not SG. And I want to prove grass is not wet. That means show that not GW is true. Are you all with me?
Yes.
Okay? So now what am I going to do? I'm going to convert all of these into clausal form. I negate this first, convert it to the clausal form. When I negate this, it will become GW, and I convert it to clausal form, it will still be GW. Okay? So this becomes not GW or R or SP. Easy in these cases. This is not R or TH. This is not SP or TH. This is not TH or SG. This is not SG. And then this one I negate it first. and then convert into clausal form. Remember, you first negate and then convert into clausal form. If you convert into clausal form and negate, you do two mistakes. Actually, in fact, if you convert into clausal form and you negate, then it's no longer in clausal form. Right? Okay. So basically, you can negate first and then convert into clausal form. That's your clauses now. So just do a series of resolutions. Now the interesting thing, of course, as you saw in the example here, you started with the blue guys, right? And then you got J and W or not W or J, you got not W. Now you decided to resolve not W with W or J. It's as if it's not just the blue guy. Anything that you resolve is also a theorem now, which makes sense. Okay? It's not that the empty clause must come only from the blue guys. In fact, if the empty clause comes directly from the blue guys, I mean, sometimes it can, but in fact, especially if the empty clause comes just from the blue guys without not J, that means the original knowledge base is inconsistent to begin with. Okay? What you're really basically looking for is find some pair of clauses which when resolved gets you empty clause. Where these pair of clauses can be either from the original set of clauses or from clauses that have been derived in the previous steps. Right? That's where it becomes interesting. Okay? So, now, look at this. So I'll show you, 8 trays. Since I'm magical and I have, the animation power, I can show you exactly one set of resolutions that get you empty class. Okay, but if you do it, you keep doing it until you find an empty class. Okay, and it's not because you're stupid. It's because this is a search problem. Okay, in a search, you just have to consider all possibilities until you find the goal. Okay, here is one. No, it's actually not a bad idea to start the first resolution with something that involves the goal. Not a bad idea. Okay, but let's not talk about it right now. So in this case, GW or not GW or RSP, I got RSP, and then I resolved RRSP to not RRTH, I got THRSP. I resolved THRSP and not THRSG, I got SGRSP. I resolved SGRSP and not SG, I got SP. I resolved SP or not SP or TH, I got TH. I resolved TH or not TH or SG, I got SG. And I resolved SG or not SG, I got empty class. Okay, I basically did something and I got an empty class. The important thing is making sure that each of the steps is actually a right resolution. Okay. Do you see what I'm saying? Now, you see this in this problem, which is reasonably obvious to you, you still needed a huge number of resolutions. So it's very easy to get lost. So you just have to hope that I won't give you this problem on like a short time test. But writing a program to do theorem proving is not a problem. Not a problem at all. Because it's just search and you know how to write search algorithms. Okay? Okay, so that's your empty clause. And when you do get an empty clause, it must then mean that I just proved that grass is not wet. Okay? So is there search in inference? Yes, there is search in inference. Because you could have done a whole bunch of other resolutions which don't go anywhere. Does anybody remember anything we talked about in this class about doing useless inferences?
Forward and planning.
Yeah, and lots of things, but the BBC joke, Sherlock Holmes and Watson. You should be thinking about it as you do this. Watson was doing resolutions for the heck of resolutions, and Sherlock Holmes said, well, the only resolution that actually mattered is to realize that somebody swiped our tent. Okay? And so we talked about it long back, and I brought that up specifically to tell you that theorem proving involves search. And I'm just, basically keeping my promise by showing that in fact even as simple a thing as propositional theorem proving does involve search. Okay, here I just showed you one branch. Okay, so let's look at what is the actual algorithm for search. This is what it is. Okay, so convert the database into clausal form and knowledge base into clausal form. Let's get a bunch, you'll get a set of clauses. Let's call that DC. That whole entire set of clauses is DC. It's a database, of clauses. Now negate the goal and then convert it into clausal form. You'll get a goal database, DG. Now the full database is DC plus DG. DC union DG, which is basically the union of all the clauses from the original knowledge base and the negation of the goal. You have now a database, okay, of some K clauses. Okay, then the loop starts. Select a pair of clauses C1 and C2 from D. Okay, and resolve C1 and C2, get C1, 2. Okay, of course, some clauses cannot be resolved at all. So you must select clauses that are resolvable and resolve them and you get resolved clause C1, 2. Okay, if C1, 2 is empty, you say, yay, I'm done, and then you stop. If not, you add C1, 2 to D. It's a new class, so D has now become fatter. Continue the loop. Okay? Now, the interesting, and so if you fall out of this loop, that means somehow you considered all possible pairs that can be resolved. So there's no point in resolving the same pair again and again and again to see maybe they'll do something different, right? Right? Okay? So if you resolve it once, you resolve it. Okay? So if you make sure that you don't do a resolution more than once, then eventually you'll fall out of this loop. If you fell out of this loop, that basically means you could not prove the theorem. You could not prove the theorem. Remember, if the theorem was true, then you would never fall out of loop, because at some point of time you'll get an empty class. If the theorem was not true, then you will fall out of the loop, and then you say the theorem can't be proved. There's an asymmetry in theorem being true, the one that you're trying to prove being actually true versus being false. Being false means it's not actually a theorem. Okay? And you are actually better off if what you're trying to prove is actually provable, because you'll get done in this loop itself. If not, you'll have to come out of this loop. Remember, for first order logic, I said this is propositional logic, right? It turns out for the propositional logic, the complexity of this algorithm is exponential. Because in the worst case, whether you come out of here or here, in the worst case, you do exponential amount. Okay? What's interesting is, in the case of propositional logic, there is something called falling out of the loop. Because you will eventually have completed all resolutions, and no more to be done. And so you say, well, no more resolutions can be done. I still haven't proved the theorem, so the theorem can't be proved. If you are talking about first order logic, you at least have one interesting intuition. First order logic can be converted eventually to propositional logic. I sort of said that. I will tell you again formally how to do this. But when you do that, you will get an infinitely large knowledge base in the propositional logic. If you have an infinitely large knowledge base in the propositional logic, you will never fall out of the loop. There's always some more stuff to be done. Which is why in the first order logic, if the theorem that you're trying to prove happens to be actually true, you would, in finite number of resolutions, get an empty class. If not, you have to fall out of the loop. And for a first order logic, there is no falling out of the loop, because you have infinite number of resolutions to be done. Which is why, and this is a pretty deep point, which is why in first order logic, the theorem proving is semi-decidable. It is decidable if the theorem that you're trying to prove is actually true. Okay? And if it is false, then the algorithm doesn't even end. It never ends. Okay? Of course, both theorem true, theorem false become hard in first order logic because you have much larger databases from a propositional logic point of view. Okay, but there is an asymmetry for theorem not true versus theorem true. Theorem true is the easy case always. In the propositional logic, you can see that. Okay, so that's the asymmetry is something that you understood by looking at this. Okay, there are other ways of understanding the semi-decidability of first order logic, but this is one good way. The other question, of course, is there is search clearly. What is the order? The search basically is a loop here. I'm selecting pairs and resolving them. Okay. Now the interesting thing is, when I say search, can I do depth first versus breadth first? Yeah, of course, you can if you want. Okay. So the interesting thing would be you can give each of these clauses a level. Each of the clauses a level. Okay. And then, so all the clauses in the initial database have a level 0. Any clause which is a resolvent of clause at level L1 and clause at level L2 will get the max of L1, L2 plus 1 as its level. If your parents both are at level 1, then your level will be 2. If one of your parents is level 1, another is level 15, then your level is 16. Okay? Then you have clauses, the level of the clause is the depth of the clause. You can do breadth first versus depth first search. Do you care whether it is depth first or breadth first? So for example, I showed you a proof here. Maybe there is a shorter proof. You care. In general, you don't. Professional mathematicians say we would like an elegant proof. And typically, elegant means the one I came up with, not the one the other guy came up with. Okay? Right? But in general, really, it's just you're doing this for a living. You want to see whether or not G is, is true. And, if you can get an empty clause, when you add not G to it, you're done. It doesn't really, you really don't care about how many resolutions you did. And the number of resolutions you did is, in some sense, the depth of the empty clause. There may be an empty clause at depth 4. There may be an empty clause at depth 17. There may be an empty clause at depth 35. You don't care. All of them are equally good for you. Okay? So this is why, in fact, you don't do a star search for theorem proving unless somebody tells you that you get marks for doing it the shortest proof. Then you want to care about that. Okay? The other question, of course, is, you have multiple pairs that can be resolved. At any particular point of time, there are many pairs saying, pick me, right? And if it's breadth first, you can do it one way. If it's depth first, you can do it the other way. I just now told you depth first, breadth first, who cares? It really doesn't matter. The length of the proof doesn't matter. And what I really care about is getting there. So the question is, what pair of clauses should I be resolving such that I'm more likely to go to the goal state? The goal state. For us, goal state is empty clause. Okay? So here are the heuristics. So for this kind of a search, heuristics look like this. And you need to understand, so this doesn't look like A star search heuristics. But this is not A star search. You did not need to do A star search here because you don't care about the shortest proof. It's still search. Okay? So here are two heuristics. Heuristic 1 basically says at least one of C1 or C2 must have support from the goal. And the support from the goal is defined recursively. Every clause in DG has support from goal. Okay? And any clause that is derived from from a clause that has support from the goal also has support from the goal. It's like royal blood. Okay? Set of support says when you are resolving clauses, make sure that at least one of them has connection to the goal. Which sort of makes sense because eventually you expect that the empty clause comes because of goal being inconsistent with the database. You see what I'm saying? So it cuts down the number of resolutions you will consider. It's cutting down the branching factor. Right? Without this, you would have considered some resolutions which you won't even consider now. Now the question is it complete? That means, would you be able to prove the completeness? I can think of in two ways. One is, would I be able to prove all theorems that I could prove before? The second is, would I be able to find all the proofs that I could find before? Of these two, the second doesn't make any sense for us. Why do I care about the exact proofs? I just want to be able to prove everything that I proved before. And in that sense, it is in fact complete. That means every theorem that you could prove before, you can still prove, even if you just stick to the set of support resolvents. That means one of the clauses must have royal blood, or the gold blood. And the gold clauses have gold blood, and any clause that is derived with one of its parents being a gold blood clause will have gold blood. Okay? This is a pretty darn good idea. You cut down the humongous amount of branching factor and still are getting completeness. Okay? Clearly, it might sometimes actually get you longer proofs. So for example, if my original knowledge base had A and not A, right? And then I'm trying to prove some very complicated theorem. If you allowed A and not A to be resolved, you would be done right away. But I won't, because original knowledge base is A and not A. Neither of them are goal clauses. So you would never resolve them. So you will find some roundabout way of finding the empty clause. So you'll get a longer proof, but you will get a proof all the same. Okay? Here is a different idea which turns out to be even faster in terms of cutting down the branching factor, but it turns out that it crosses into incompleteness. Okay? Where this one is saying at least one of the clauses, C1 or C2, must be from D. Must be from D. That means you will never be allowed to resolve two clauses which have been derived after you started. At least one of the clauses must be from the original set of clauses, DI plus DG, DC plus DG. Okay? It turns out this form is not complete. But many provers actually use it. Classic example is Prolog, which is a theorem prover. And Prolog uses linear input form. And it's not complete. But as I said, just as we said, admissibility versus inadmissibility, we understand it, and then we just go with inadmissible heuristics once in a while anyway, because first live before being optimal. Okay? The same situation here. This one is complete, this is not complete, but this cuts down the branching factor even more. So you go with it. Okay? We'll stop here.